In this next video, we're going to look at u-substitution, but with definite integrals this time. So it's going to be very similar. A lot of aspects are going to be very similar. We know how to treat definite integrals. It's going to be a slight difference because when we're changing that u, we also need to think about changing the upper and lower bounds of those integrals. So we're going to take a look at this. So let's start with the definition of the rule. Substitution rule for definite integrals. If g prime is continuous on the interval a to b, and b is continuous on the range of g of x equals u, then the integral from a to b of f of g of x times g prime of x is equal to the integral of g of a to g of b of f of u du. Let's just jump right to an example. I'm again not going to prove this on this video, so let's take as the first example the integral of 0 to 3 of 2x times x squared plus 3 to the fourth power dx. So coming off that last video, we should be, I think, pretty comfortable with, excuse me, what we're gonna do here. So I'm gonna let u equal that inner function, the x squared plus 3. The power of 4 is obviously the most, that is the outer function here, that is the more complex element. It's the thing we don't want to have to do. We don't want to have to multiply that thing out 4 times over. So we'll avoid it by calling it a u. Therefore, du would be equal to 2x dx. And so we can see that that 2x d, that should be a dx, not du. Sorry, I was getting ahead of myself. I want this initial problem to be a dx, otherwise the whole exercise is quite pointless. And so we have that 2x dx, which is exactly the du. So we could go ahead and replace that. But the problem is, if I replace it right now and leave the 0 and the 3 there, this is now incorrect. Because the same way we talked about in the last video, the second we change one thing to a u, we've got to have everything in terms of that new variable. Same has to be true for the bounds. We just didn't have any integration limits before, so we didn't have to worry about that. But now we do, so I cannot write that 0 and 3 on my integration sign. I need to leave those off. So what can we do? Well, we can convert those as well. If we think about the 0 and the 3, that's an x is equal to 0 and an x is equal to 3. We can plug those in for our u equation. U would be equal to 0 squared plus 3, which is equal to 3. And then we would have u is equal to 3 squared plus 3, which is 12. So I can come back here and we want everything in terms of u. Well, this x value of 0 corresponds to a u of 3, and the x value of 3 corresponds to a u value of 12. And so I can make that replacement. And then these two things are still equal to one another. And so now we can do the same integration that we're used to, 1/5 u to the 5th. I don't need to write that plus c there because it's not an indefinite integral. We are just looking at one form of the antiderivative because that's all we need. And the other thing we don't have to do this time is we don't have to convert back to an x. We don't have to get back to x because we are plugging in our values of 3 and 12, which we have already fixed to match with the u that we've changed to. And so now I'm going to plug these in. So 1/5 times 12 to the 5th power minus 1/5 times 3 to the 5th. And just need to simplify or evaluate at this point, so I'm sure we can all look at this and we know exactly what the answer is just by doing it in our head. I've used a calculator to help me to make sure I have it right. And it's the number that we would all expect, 49,717.8. So again, 12 to the 5th is very easy to do in our heads, but feel free to use a calculator when we have these bigger numbers. Now, you might be looking at this saying, well, why did we bother changing those limits of integration? Why didn't we just plug back in for x after we integrated, like we had done before, like we did with our indefinite integrals? And the truth is we could. That's another way we can approach this problem. So let's do it that way too. Let's see another approach to this problem. So we're trying to solve this definite integral. I'm going to do it down here just so I can keep it close to my other work so I can refer to my other work. We're trying to do this definite integral. We, the first time around, changed over to u's like we would expect. We had to change those limits of integration because we left them there. We did that integration. We left in terms of u because we had already changed those limits. But what if I instead say, well, let's just treat it like we did in the last video. let's treat it like an indefinite integral. Well, we're going to do the same thing. We're going to say that u is equal to x squared plus 3, and so this is going to give us u to the fourth, and then 2x dx is du. We get to the same place, it's just I don't have those upper and lower bounds anymore. And then I'm going to get to the same antiderivative. But this time, because it's an indefinite integral, I have to put that plus c. That is the first difference. Also notice there's no numbers I'm plugging in for because we have not left that 0 and 3 there. I never stated that these two lines were equal. Let me try and get my computer to switch colors there. Right here, I've never stated those two lines are equal. Where those red equals are, that is completely false. An indefinite integral is not equal to a definite integral. And the second I go changing over to u's, if I have not changed those upper and lower limits, I've got to take that u and I've got to switch it back. I've got to plug that x squared back in for my u. Plus c, I don't need the dx. And so that is actually my indefinite integral. It's got to have that x plugged back in. I have no choice. I have to do that on the indefinites. And now that I have that indefinite integral, I'm going to use that to solve my definite integral. I put the equals in the wrong spot. I wanted to have that on the line above. Because this definite integral has to be the same thing as the indefinite integral evaluated between the 0 and the 3. So I can't state that these two sides of the red line are equal. My computer would speed up here. I can't state that these two sides are equal. What's on the top and on the right here, this is a definite integral. Underneath the red box is an indefinite integral. We can use that to assist us in finding the definite integral. They're definitely related. But these two things are not equal. These two things are not equal. These two things are not equal. We can take the indefinite integral, we can use that to get an antiderivative, then we can use one of those antiderivatives, not the most general form, we're dropping the c, we can use that antiderivative to evaluate between 0 and 3. So continuing with my work, when we plug in the 3 and the 1 and the 0, we get 1/5 times 3 squared plus 3 to the 5th minus 1/5 times 0 squared plus 3 to the 5th. And these numbers are going to look very, very familiar. We have a 1/5 here. We have 3 squared, which is 9 plus 3. That's 12 to the 5th. And then 1/5 times 0 plus 3 is just 3 to the 5th. Notice those are the exact same numbers we had just a second ago. And so we get to the same place. It is just a matter of whether we're plugging in before or after. If we are changing those integration bounds, or if we're leaving it, if we're going to work with the indefinite integral, and we're going to use that indefinite integral to help us calculate the definite. So very, very little difference than the last video, very little difference to the indefinite integrals. We can in fact work with that indefinite integral. We just have to remember to plug in our numbers, plug in our values. Let's take another example. Let's take the integral from 0 to the natural log of 1 plus pi of e to the x times cosine 1 minus e to the x dx. I'm going to keep the parenthesis behind the e. All right, so my first step is to change over to some u's. Because I don't know how to integrate this thing, I'm going to let my u equal the inner function, the 1 minus e to the x. So du would be equal to a negative e to the x dx. So if you wanted to solve for the dx to replace, you could. Dx would be equal to du over negative e to the x. But I can't just replace the dx and the x terms. I've also got to replace those limits of integration. So we have an x is equal to 0, and we have an x is equal to the natural log of 1 plus pi. And so I'm going to plug these in for my x. U is equal to 1 minus e to the 0. Well, e to the 0, anything to the 0 is 1. That would give us 1 minus 1 or 0. So the 0 actually stays in the same place. but we had to calculate that. The natural log, I'm guessing that one's probably going to change. Let's see what it is. 1 minus e to the natural log of 1 plus pi. And so remember, if we have a exponential to its own logarithm, they essentially kind of cancel, or we're left with what was inside that logarithm. So 1 plus pi. And 1 minus 1 is 0, and then we're left with a negative pi there. So this integral has to be equal to negative, the 0 was at 0, and then the natural log was that was the pi. So 0 to negative pi, those were what we just calculated. E to the x cosine of u du over a negative e to the x. A couple things I could do here. For one, sometimes we don't mentally, we kind of get a block of integrating to a smaller number. So if we wanted to switch this, we could go from negative pi to 0, and that would mean we'd put a negative out front. The e to the x's would cancel, but notice there's a negative there, so that's actually going to turn that back into a positive. And then we have cosine u du. Didn't have to make that switch. We could have left it 0 to negative pi, and then we could have gone from, we would have had just a negative. It doesn't matter at all. And so now when we go to integrate this, the antiderivative of cosine is sine. We don't need a c because we have numbers that we're plugging in. We have the definite integral. And so we're going to plug this in. Sine of 0 minus sine of negative pi. And sine of 0 is 0. And sine of pi is 0. We get 0 minus 0, which is just 0. So we get 0. It's perfectly balanced above and below the x-axis. And 0 is an absolutely acceptable integral to get. Let's do a third and final example. I'm not going to do very many of these, and because we did a bunch with the indefinite integrals, and also notice that one I only approached it from the definite integral side where I was changing those limits of integration. I'm going to do the same thing here, not because it's better or worse, it's just different, and we don't have as much practice with it. We have gotten a lot of practice with u-substitution in indefinite integrals, and so I want to concentrate on changing those limits over, but it does not matter. All right, so here I see a function times another function, but this second function, cosine of sine, has a composition. So I'm going to let my u equal that inner function, the sine x. So du is equal to cosine x dx. And so as I go to replace my things here, cosine x dx is just u, cosine of sine is u. But I still need to change those upper and lower limits, so let's do that next. We have an x value of pi over 2, and we have an x value of negative pi. And so u here, sine of pi over 2, that's equal to 1. And then here, sine of negative pi is 0. We do want to make sure that we get them matched up right, so I always kind of do it top and bottom to remind myself this is literally top and bottom. But do always make sure that the pi over 2, that's the one we started with, so we got to make sure we get the corresponding, in this case 1 on top, and then the negative pi, the 0 on the bottom. We need to make sure we're consistent, we don't switch those on accident. Now we can do our antiderivative, which once again is sine. Sine of u, and we're integrating from 0 to 1. This time we're not just going to get 0, sine of 1 is some irrational number minus sine of 0, that is just 0, and so our answer is sine of 1. So same u-substitution that we were working with before, we're picking that inner function, we are changing that over, we're changing the differential at the same time, but then we have an option, we have two choices. We can change those limits of integration, as we did in this example, or we could leave them the same as we did in the first example. We just have to remember if we leave them the same, we can't say they're equal. We have to say we were working now with an indefinite integral, and we'll come back and pick up with a definite later on.